Welcome back. You've sent us, well, a really fascinating collection of materials here. It's a proper deep dive into what you, as a software developer, really need to know if you're thinking about moving into building products powered by generative AI.
Yeah, it's quite the package. We're looking at like a PhD level analysis almost.
Mhm.
It covers the core ideas, the technical skills you absolutely need.
Right, and also how these products actually get made, who the main players are, and crucially, how you can actually make that career shift.
Exactly.
Yeah.
And let's be honest, you're trying to navigate a field that's not just new, it feels like it changes every week.
Uh-huh. So our goal with this deep dive then is what? To kind of cut through the noise.
Pretty much. We want to pull out the absolute core insights, the stuff you really need to get your head around to make this transition, without drowning in jargon.
Think of it as your express route to getting up to speed. A shortcut, maybe?
Something like that.
Yeah.
Getting you well informed on a pretty complex topic.
Okay, so let's start at the beginning. We hear generative AI everywhere. What's the fundamental idea? What makes it generative?
Well, the key word is creation. Unlike older AI, that might just analyze data that's already there.
Like classification or prediction?
Exactly. Generative AI is all about learning patterns, usually from absolutely massive data sets, and then using that understanding to create something entirely new.
New text, new images, code.
Code, audio, you name it. It's AI that can, in a way, mimic human creativity or even extend it sometimes.
And technically, how does it do that?
It relies on specific kinds of neural networks, things like GANs, VAEs, and the really big one these days, transformers. Often they learn using unsupervised or self-supervised methods, meaning they don't always need neat labels on all the training data.
Okay. And these LLM-based products and services, that stands for large language model, right? How do they fit in?
Spot on. LLM-based products are basically applications built around these large language models.
Which are based on that transformer architecture you mentioned.
Correct. They're deep learning models, usually transformers, trained on just vast quantities of text data. This gives them this incredible ability to understand and generate text that feels, well, human.
So like chatbots, but much more advanced.
Way more advanced. Think sophisticated chatbots? Yeah. But also tools that write marketing copy, generate code, translation services that sound natural.
AI-powered search, maybe. That goes beyond just keywords.
Definitely. And we're seeing them pop up in specialized fields too. Healthcare, finance, law automating tasks, helping professionals.
So if you, our listener, are making this move, shifting from maybe traditional software development into this Gen AI space, what does the day-to-day look like? It sounds different.
It is a shift, yeah. You're not just coding in isolation anymore.
Right.
As a developer focusing on Gen AI, or LLMs, well, you're involved in picking the right pre-trained models, maybe fine-tuning them for specific needs.
Fine-tuning, we'll need to unpack that later.
We will. You're also designing and managing the whole AI pipeline, getting data ready, deployment, monitoring, the whole life cycle.
And I hear a lot about prompt engineering.
That's a huge one. Crafting the right inputs, the prompts, to get the LLM to give you the output you actually want. It's a skill in itself.
You also mentioned RAG earlier, Retrieval-Augmented Generation.
Yep. Integrating models with external data sources. We'll definitely dig into that. And then there are the tools.
The frameworks, like TensorFlow, PyTorch.
Those are the big ones for deep learning. Plus libraries like Hugging Face Transformers, maybe LangChain. And you need to be comfortable with the cloud platforms, AWS, Azure, GCP, because that's where these models often live.
Okay. And what does a successful career transition actually look like here? It's not just getting the job title, is it?
Not at all. Success means you've, yes, learned the skills and landed a role, but you're also effective in that role. And crucially, you're continuing to grow.
Because the field moves so fast.
Insanely fast. So adaptability, that commitment to lifelong learning, it's non-negotiable. Building a portfolio is key too, showing what you can actually do.
And networking, connecting with people.
Absolutely vital. And, it's also about seeing the bigger picture. Gen AI might automate some old tasks, but it's creating these entirely new, exciting roles for developers who have the right skill set.
Right, it makes sense. Okay, we've got the lay of the land. Let's dig into the foundations. What knowledge does a developer really need? And Python.
Seems like Python is just unavoidable here.
It really is the lingua franca of AI and ML, isn't it? Its simplicity, the incredible ecosystem of libraries, the huge community, just makes it the default choice for most things.
So step one is solid Python.
Absolutely. You need a strong grasp of the basics, data structures, algorithms, object-oriented programming, the standard libraries. That's your bedrock.
And then on top of that, specific libraries for AI. You mentioned NumPy and Pandas.
Yeah, they're fundamental for handling data. NumPy gives you efficient numerical computing, dealing with arrays, math operations. Pandas builds on that for data manipulation and analysis, cleaning data, transforming it, analyzing those big data sets LLMs need. Essential.
What about scikit-learn? I know that one from more traditional ML. Still very relevant. It covers classic ML algorithms, regression, classification, clustering. Even if you're focused on LLMs, understanding these concepts is super helpful. Plus, you might use scikit-learn for building simpler baseline models or specific parts of a larger AI system.
But for the deep learning stuff, the LLMs themselves, it's TensorFlow and PyTorch.
Those are the heavy hitters, yes. You really need to get proficient in at least one, probably both eventually, to properly build, train, and deploy these complex neural networks.
And within TensorFlow, things like Keras.
Yeah, TF.Keras is a really important high-level API, makes building and training networks much more streamlined.
Okay, even with these powerful deep learning frameworks, you mentioned understanding machine learning fundamentals is still important, like supervised versus unsupervised learning.
That's a really great point. Don't skip the fundamentals. Even with LLMs, understanding supervised learning training models on labeled data for tasks like prediction or classification is crucial.
So things like linear regression, logistic regression.
Exactly. And the core ideas behind how models learn training data, cost functions, gradient descent, that knowledge gives you a solid base.
And unsupervised learning.
Also valuable. Techniques like clustering or dimensionality reduction help you find patterns in data without labels. Great for exploring data, preparing it, feature engineering.
And once you've built a model, how do you know if it's any good?
Yeah.
Model evaluation, right?
Precisely. You need metrics. For classification, you're looking at accuracy, precision, recall, F1 score, maybe AUC.
And avoiding pitfalls like overfitting.
Critical. Understanding overfitting where the model just memorizes the training data and underfitting where it's too simple is key. That links to the bias variance trade-off.
And techniques like cross-validation.
Yep, helps you get a better sense of how your model will actually perform on new, unseen data. And underpinning all of this is data handling.
Cleaning, transforming, dealing with missing values.
All of that. Plus feature engineering, creating useful inputs for your model, and just managing the sheer scale of data you often deal with in LLM work.
Okay, let's dive into deep learning itself then. What are the must-know concepts for someone transitioning?
You need the building blocks. Understand the basic structure of a neural network. Layers, neurons, activation functions, how information flows through.
And how they learn, backpropagation.
Exactly. How errors are propagated back through the network to adjust the weights, usually using an optimization algorithm like gradient descent or its variants like Adam.
And while we're focused on LLMs, knowing about other architectures helps, like CNNs and RNNs.
It provides really good context. CNNs are dominant in image processing. RNNs and LSTMs were key for sequential data before transformers took over. Understanding their strengths and weaknesses helps you appreciate why transformers were such a leap forward.
And the practicalities of training.
Yeah, things like tuning hyperparameters, the settings you choose before training starts, using regularization techniques like dropout to prevent overfitting, choosing the right optimization algorithm. These are all practical skills for getting models to work well.
Makes sense. Now, given we're talking large language models, NLP, natural language processing, must be core. What are the essentials there?
Absolutely central. It starts with text preprocessing, getting the text ready for the model.
Like tokenization, breaking text into words or pieces.
Exactly. Tokenization is fundamental, and you need to understand how different LLMs do it. Also, stemming and lemmatization, reducing words to their root forms, and removing stop words, those common words like the or is.
And embeddings, representing text as numbers.
Crucial. Embeddings turn words or text chunks into numerical vectors that capture semantic meaning. This is how LLMs understand language. It's also key for semantic search in vector databases, which we'll get to with our RAG.
What about core NLP tasks?
Having a basic understanding helps. Things like text classification, putting text into categories, sentiment analysis, figuring out the emotion, named entity recognition, finding names, places, organizations in text, machine translation, question answering. Knowing these provides context for LLM applications.
Okay, and that brings us squarely to the transformer architecture. You called it the engine behind most modern LLMs. Sounds like something developers really need to grasp.
Oh, absolutely. The transformer, introduced in that famous Attention is All You Need paper,
Hmm.
it was revolutionary for NLP.
Because of self-attention.
That's the core innovation. It allows the model to weigh the importance of different words in the input sequence when processing each word. It's brilliant for capturing long-range dependencies in text.
And the structure. Encoder-decoder.
The original paper had both, yeah. Though, interestingly, many of the big LLMs today are actually decoder-only architectures. But understanding the concepts is still key,
Like multi-head attention.
right? Allows the model to focus on different types of relationships simultaneously. Positional encoding is another piece, giving the model information about word order, since the core attention mechanism doesn't inherently understand sequence.
Feed-forward layers, too.
Yep, standard neural network layers within each transformer block. And understanding how text gets tokenized and turned into embeddings before it even hits the transformer, having that intuition is vital for using, fine-tuning, and even troubleshooting these models.
Any resources you'd recommend for getting deeper into transformers?
Definitely check out the Illustrated Transformer blog post. It's fantastic visually. And courses on platforms like deeplearning.ai that focus on NLP and transformers are really valuable.
Okay, foundation laid. Now let's climb the stack to more advanced skills for actually building LLM products. Fine-tuning seems critical.
It really is. Fine-tuning is how you take a massive, general-purpose pre-trained LLM and adapt it to your specific needs. You train it further, but on a much smaller, curated dataset relevant to your domain or task.
Like making a generalist AI into a specialist.
Exactly. A key technique is instruction tuning. You train the model on examples like instruction, summarize this text, output, summary. This makes it much better at following commands.
But fine-tuning these huge models sounds computationally expensive.
It can be. That's why parameter-efficient fine-tuning, or PEFT methods, are so important. They let you adapt the model by only updating a tiny fraction of its parameters.
Like LoRa, low-rank adaptation.
LoRa is a very popular one, yes. And its variant QLoRa, which works with quantized models. There's also prompt tuning, adapter modules, different ways to achieve efficiency. PQA is another interesting one, adapting quantized models.
And the data for fine-tuning needs careful thought.
Hugely important. Getting high-quality instruction data is a challenge. And you have to be careful. Fine-tuning can sometimes introduce new factual errors or reinforce existing biases if the data isn't right.
Okay, so you've got your model, maybe fine-tuned it. How do you actually talk to it effectively? That's prompt engineering, right?
That's the essence of it. Prompt engineering is all about crafting the input, the prompt, to guide the LLM towards the output you want, without actually changing the model's weights.
So it's like debugging, but for language inputs.
That's a great analogy. It's a structured, iterative process. Clarity and specificity are key. Be really clear about the task, the context, the desired format, length, style.
And structure helps. Putting instructions first, using delimiters.
Definitely. Breaking down complex tasks into steps in the prompt can work well. Assigning the LLM a role, like you are a helpful assistant specializing in.
What about giving examples? Few-shot prompting.
Yes, providing a few input-output examples right in the prompt can really guide the model. That's few-shot as opposed to zero-shot, where you give no examples.
Are there more advanced strategies?
Oh, yeah. Things like chain-of-thought prompting, where you ask the model to think step by step. Self-consistency, when you generate multiple reasoning paths and take the most common answer. Plan and solve prompting, even just being explicit about what not to include.
It sounds like it requires creativity and iteration.
It does. You
Yeah.
prompt, analyze the output, refine the prompt, repeat. But it has limits. LLMs can still misunderstand ambiguous prompts.
Got it. Now, you mentioned Retrieval-Augmented Generation, RAG, a few times. How does that boost LLMs?
RAG is a really powerful technique for grounding LLMs in external, up-to-date information. Helps combat hallucination, making things up, and keeps the model's knowledge current.
So it fetches information on the fly.
Essentially, yes. During the generation process, the typical workflow starts with indexing your knowledge source, documents, databases, whatever.
Breaking them down, embedding them, storing them.
Exactly. You chunk the documents, create vector embeddings for each chunk, and load them into a vector database.
Ah, the vector database again. For semantic search.
Precisely. When a user query comes in, you embed the query and use the vector database to find the most semantically similar chunks from your knowledge source.
And then?
You take those retrieved chunks, combine them with the original query, and feed that whole augmented prompt to the LLM. The LLM now has relevant context to draw from when generating its answer.
Are there different flavors of RAG?
Yes. There's naive RAG, which is that basic index retrieve generate flow. Then advanced RAG adds optimizations, maybe smarter indexing, re-ranking retrieve results, compressing context before sending it to the LLM. Tools like LangChain and Llama Index offer lots of these capabilities.
And modular RAG.
That's about building RAG systems with more interchangeable components. Thinking about the system more flexibly, there are even novel approaches emerging like QuimRAG.
So RAG and fine-tuning, they really move beyond just using an LLM as a black box, don't they?
Absolutely. You're integrating them into larger information systems. It requires skills in data pipelines, managing knowledge sources, understanding vector databases.
Speaking of vector databases, let's focus on them for a moment. What makes them tick?
Their specialization is storing and querying high-dimensional vectors, those embeddings we keep talking about, based on semantic similarity, not just keywords. Crucial for RAG.
What do you look for when choosing one?
Key things are scalability, can it handle your data volume? Performance latency, throughput. The indexing methods they use, like HNSW or IVF, affect search speed and accuracy.
Deployment options, cloud versus self-hosted.
Right, integration with frameworks like LangChain. And, of course, cost is always a factor.
And there are several players in this space.
Oh, yes. Pinecone, Milvus, Weaviate, Chroma are some of the well-known ones. We actually have a table 1 in the source material, comparing these across key features, architecture, use cases, worth looking at.
Okay, so we have the model, we're prompting it, maybe using RGA. How do we actually measure how well it's doing? LLM evaluation.
Evaluation is tricky, really tricky. Because the outputs are often open-ended text, a single number doesn't tell the whole story. You need a multifaceted approach.
Are there automated metrics?
There are. Some older ones like BLEU and Rouge look at word overlap with reference texts. Useful, but limited for semantic meaning.
Newer ones are better.
Embedding-based metrics like BERT score compare the meaning using contextual embeddings. Learned metrics like COMET are actually trained models that try to predict human judgments of quality. Perplexity is another common one, measuring how surprised the model is by the text.
And benchmarks, standard tests.
Yes. Several benchmark datasets and frameworks exist to compare models, though you have to be careful about how they're implemented and potential overfitting to the benchmark itself.
Like MMLU?
MMLU tests knowledge across dozens of subjects, multiple choice format. ALM is very comprehensive, looking at accuracy, calibration, fairness, lots of metrics across different scenarios. Big Bench is a massive collaborative effort with diverse tasks.
And tools to run these?
Alether AI's LM evaluation harness is a popular framework for running evaluations reproducibly.
But automated metrics aren't everything.
Definitely not. Human evaluation is still often considered the gold standard for subjective qualities, coherence, relevance, safety, style. But it's slow, expensive, and subjective.
I've also heard of LLMs evaluating other LLMs.
Yeah, LM as a judge. Using a powerful model like GPT-4 to score the output of another model. It's faster than humans, but raises questions about bias and reliability. Is the judge model biased?
It's complex, and it seems like consistent reporting is lacking.
That's a major issue. Leading developers don't always report results on the same benchmarks or using the same methods, making direct comparisons hard. Table 2 in the notes summarizes some key benchmarks: MMLU, HLM, Big Bench, LM Evil Harness.
Okay, one more critical technical area before we move to the product lifecycle. Responsible AI, fairness, bias, transparency. This feels incredibly important.
It's paramount. Given the potential societal impact of these models, integrating ethical considerations from the very beginning is not just nice to have, it's essential.
Let's break it down. What does fairness mean in this context?
It's about ensuring the AI system doesn't lead to discriminatory outcomes. There's group fairness, checking if the model performs equally well across different demographic groups, and individual fairness, making sure similar individuals are treated similarly.
Are there legal concepts involved?
Yes. Ideas like disparate treatment, intentionally discriminating, and disparate impact, unintentionally having a discriminatory effect, are relevant. Defining fairness is often highly context-dependent.
And bias, where does that come from?
Bias refers to systematic errors that cause unfair outcomes. It can creep in from many places. Systemic societal biases, biases in the data used for training, sampling bias, representation bias.
Algorithm bias, human bias in labeling or design.
All of those. And interaction bias, how users interact with the system. LLMs trained on the internet inherit the biases present there, which is a huge challenge.
Transparency and explainability seem related. Understanding why the model does what it does.
Crucial for trust, debugging, accountability. But honestly, it's a major hurdle with these huge, complex LLMs. They're often quite opaque, and current transparency from developers is often lacking.
So how can developers mitigate bias?
There are techniques at different stages. Pre-processing, modifying the training data itself, relabeling, resampling, reweighting. In processing, changing the learning algorithm or its objective function to incorporate fairness constraints.
And post-processing.
Adjusting the model's predictions after training. This is often seen as a last resort because you're not fixing the underlying problem.
Are there frameworks to guide this?
Yes, the NIST AI Risk Management Framework is a key one in the U.S. The ACM FACT community focuses specifically on fairness, accountability, and transparency research. But it's complex. Fairness is nuanced, LLMs are opaque. It's a critical competency for developers.
Absolutely. Okay, let's shift focus now to the actual process of building an LLM product. It starts with an idea, right? Ideation and use case identification.
Exactly. You need to figure out where LLMs can provide real value. It's about moving beyond generic ideas like, let's build a chatbot, to finding specific problems in specific domains where this tech can make a difference.
Are there structured ways to brainstorm?
There are frameworks, often adapting standard product development phases like discover, define, develop, deliver, but maybe using AI prompts to help product managers brainstorm. LLMs themselves can be brainstorming partners, though maybe less so for defining scope or evaluating feasibility.
The key is the value proposition.
Absolutely. What problem are you solving?
Right.
Why is an LLM solution better than what exists? You need a deep understanding of user needs.
Once you have the idea, the user experience, the UX must be different for AI interfaces compared to traditional software.
Hugely different. You have to consider human-AI interaction, HAI, principles. LLMs aren't deterministic. They can make mistakes. Their reasoning isn't always clear.
So managing expectations is key.
Crucial. Be upfront about capabilities and limitations. Handle imperfections gracefully. Transparency, where possible, about how the AI works helps build trust.
Giving users control, feedback mechanisms.
Essential. Let users guide the AI, correct it, rate its outputs. Think about how Google Gemini lets you tweak response length or tone.
What about the interface itself? Conversational.
Conversational interfaces, CUIs, are common, but sometimes a hybrid approach missing graphical elements, GUI, in conversation works best. It really depends on the task.
So human-centered design, but adapted for AI's quirks.
Exactly. Acknowledge the probabilistic nature, the potential for errors, make transparency, user control, and feedback central to building trust and utility.
Right. Now, deployment, getting the application out there. Cloud versus edge seems like a major decision point.
It is. The cloud is dominant right now, especially for training, fine-tuning, and heavy-duty inference.
AWS, Azure, GCP, the big players.
Yep. AWS has SageMaker, Bedrock with models like Claude and Llama. Azure has Azure ML, the Azure OpenAI service with GPT models. GCP has Vertex AI with Gemini, PolM, Gemma models, and TPUs.
What drives the choice?
Often existing infrastructure, which specific models you need access to, potential provider lock-in, scalability requirements, MLOps capabilities, and definitely cost. Using spot instances can save money.
And edge AI, running models on devices.
That's the other side. Deploying smaller, optimized models directly on smartphones, IoT devices, laptops.
Benefits being lower latency, privacy, offline use.
Exactly. But the challenge is optimizing those huge models to fit on resource-constrained hardware. Tools like TensorFlow Lite, on-NX runtime, hardware like NVIDIA Jetson help. We're even seeing on-device RAG emerge.
We have Table 3 in the notes comparing the cloud providers' AI services, right?
Yes, it lays out their key services, featured models, MLOps strengths, and pricing considerations. Helpful comparison.
Okay, you mentioned MLOps again, but specifically LLMOps. What's the difference from traditional MLOps?
LLMOps adapts MLOps practices for the unique lifecycle of LLM applications. It's not just a buzzword. There are real differences.
Like the starting point, pre-trained models.
Right. Often you start with a massive foundation model, so the focus shifts from training from scratch to adaptation, prompt engineering, fine-tuning, RAG integration, using tools like LangChain or Llama Index. Managing vector databases is part of it.
Evaluation is different too. More human feedback.
Yes. Things like reinforcement learning from human feedback, RLHF, play a bigger role alongside automated metrics. Cost focus might shift more towards inference, which can be expensive at scale.
And versioning needs to be more rigorous.
Critically important. You're not just versioning code and models, but also prompts, evaluation data sets, the knowledge bases used for Raji. It's more complex.
Table 4 in the notes compares LLMOps and traditional MLOps on these points.
It does. It highlights those differences in starting point, adaptation methods, Data focus, evaluation, cost drivers, versioning needs. Really useful for understanding the shift.
So what are the core LLMOps practices then?
Things like solid data management, prompt engineering pipelines, reproducible fine-tuning workflows, model governance using tools like MLflow, efficient serving, BentML, NVIDIA Triton, continuous monitoring, evidently AI, managing human feedback loops, resource management, and always responsible AI checks.
And finally, performance optimization, making these things run fast and cheap.
Absolutely critical for usability and cost effectiveness. We care about things like time to first token, TTFT, output tokens per second, OTPS, end-to-end latency.
How do you optimize? Model compression.
That's a big one. Quantization, using lower precision numbers like INT8 or even INT4. Pruning, removing unimportant model weights. Knowledge distillation, training a smaller model to mimic a bigger one.
What about the attention mechanism itself?
Techniques like flash attention make the core computation faster and more memory efficient. Sparse attention focuses computation on important parts.
Batching requests. Caching.
Yes, batching requests together improves throughput. KV caching stores intermediate results from the attention mechanism to speed up generation, especially for long sequences.
Hardware acceleration. Distributed computing.
Definitely. Using GPUs with tensor cores, Google TPUs, optimized runtimes like NVIDIA Triton, libraries like Tensorite, and distributing the model across multiple chips using model parallelism, pipeline parallelism, or tensor parallelism.
Even prompt design matters for performance.
It can. Concise prompts, breaking down tasks, managing context window length, it all contributes. But there are trade-offs between these techniques. You need to evaluate based on your specific application needs.
Okay, massive amount on the tech and process. Let's zoom out again. The generative AI ecosystem. What does the industry landscape look like?
It's dynamic, characterized by incredibly rapid growth, huge investment, and fierce competition.
The big tech companies are heavily involved.
Absolutely. Google, Microsoft, Meta, AWS, Anthropic, OpenAI, they're all major players, pushing research and building large models. And don't forget NVIDIA. Their GPUs and software like CADA and TensorArt are the enabling infrastructure for almost everyone.
What about startups?
A vibrant ecosystem there, too. Hugging Face is huge as a platform and community hub. Companies like Perplexity AI innovating in search, AI21 Labs, Jasper for content creation, Cohere focus on enterprise, Glean for enterprise search, plus all the vector database providers we mentioned, Pinecone, Milvus, etc.
And the market is growing fast.
Explosively. Projections are talking hundreds of billions in spending by 2025. Gartner predicts a huge jump. A lot of that is hardware costs, though. We also see high failure rates for proof of concepts trying to become real products.
What are the main applications and business models?
Content creation, chatbots, translations, search, data analysis are common. More advanced uses in drug discovery, recommendations. Business models range from API access, subscriptions, to embedding AI features in existing software.
So it's a mix of hype and real progress.
Exactly. Amazing advancements and investment, but also real challenges in standardization, regulation, just making these things work reliably and cost-effectively in practice. Developers need to navigate this constantly shifting landscape.
And where is the tech heading? What are the emerging frontiers?
Several key trends. Multimodality is a big one. Models that understand and generate combinations of text, images, audio, video. Think asking a model about a chart and text in a document.
That enables richer interactions. What else?
Agentic AI. Autonomous agents that can reason, plan, use tools, access memory, and carry out complex tasks with minimal human input. This is expected to grow significantly, potentially transforming knowledge work.
And running models locally, on-device AI.
Yes, smaller, optimized LLMs running on-edge devices for privacy, low-latency offline use. That requires expertise in model optimization.
AI copilots seem to be everywhere already.
They are, augmenting human capabilities in coding, writing, design. These trends point towards AI becoming more integrated, more context-aware, more autonomous. Future developers might need skills in orchestrating these systems, handling multimodal data, designing agents.
With all this power comes responsibility and regulation. What's happening on that front?
There is definitely increasing global scrutiny. Safety, fairness, transparency, trust are the big themes.
The EU AI Act seems significant.
Very. It takes a risk-based approach. Strict rules for high-risk AI systems, transparency requirements for general-purpose models like LLMs, and bans on certain applications deemed unacceptable.
How does the U.S. compare?
More fragmented so far. There's a presidential executive order focused on safety, referencing the NIST AI risk management framework. But regulation is largely happening at the state level, with various bills emerging with different scopes and requirements.
How about existing laws? Data privacy.
Absolutely. GDPR in Europe, CCPA California, these impact AI significantly, especially regarding training data that contains personal information. Consent, purpose limitation, data subject rights are key. Remember, Italy temporarily banning ChatGPT over privacy concerns.
Other concerns driving regulation: copyright, deepfakes.
Yes, copyright infringement by models trained on copyrighted data is a huge issue.
Yeah.
Potential for political deepfakes, model vulnerabilities, these are all pushing the need for rules and ethical guidelines.
So developers need to be proactive about compliance.
Definitely. Documentation, data governance, transparency reports, risk assessments, and just staying informed about this evolving landscape are becoming part of the job.
Okay, let's bring it back to the developer looking to make this transition. We've covered the tech, the industry, the rules. What's the strategic roadmap? How do you actually do it?
It needs a plan. First, building expertise. Take a structured approach to learning.
Online courses, specialization.
They're sure. Platforms like Coursera, deeplearning.ai, EDX, Udacity have great offerings. Stanford's NLP specialization, Andrew Ng's courses on Gen AI, LangChain. University programs too, if that's an option.
Self-study, reading papers.
Essential. Keep up with research papers from conferences like NeurAPS, ICML, ACL. Read technical blogs from leading companies and researchers. RCIB is your friend. Books help build foundational knowledge. Certifications can also help validate skills.
And continuous learning is key, given the pace.
Nonstop. You have to keep learning.
But knowledge isn't enough, right? You need to show you can do it, the portfolio.
Absolutely critical. Practical application through personal projects or contributing to open source is how you demonstrate hands-on skills. Aim for diverse projects.
What kind of projects are relevant?
Build a RAG system. Maybe question answering over your own documents using LangChain and a vector DB like Chroma. Fine-tune an open source LLM Llama 3, Mistral, Gemma for a specific task like summarizing dialogues or generating code.
What about AI agents?
Good one. Build an agent for a multi-step task using something like LangGraph or Crew AI. Maybe analyzing financial reports or planning a project. Multimodal projects, image-to-story generators. Even just deploying an LLM app as an API with monitoring.
And showcase this work well.
On GitHub, definitely.
Right.
With clear documentation, clean code, explaining your process. Projects showing advanced techniques, specific fine-tuning methods like QLaRA, sophisticated RAG, agent design really stand out.
Networking seems crucial too, connecting with the AI community.
Immensely valuable. For learning, finding opportunities, staying current, finding collaborators.
Conferences, online communities.
Conferences like NeurAPS, ICML, FACT are great, but can be expensive. Look for volunteer opportunities or grants. Online, the Hugging Face Hub and Discord are fantastic. Subreddits like machine learning, specialized discords.
Local meetups, hackathons.
Excellent for hands-on experience and meeting people locally, and contributing to open source on GitHub or Hugging Face is a great way to learn, collaborate, and gain visibility.
Okay, you've built the skills, the portfolio, the network. Now you need to market yourself. Resume and interviews.
Exactly. Communicating your value effectively is vital. Your resume needs to scream LLM Gen AI developer.
How? Keywords. Quantifying achievements.
Use relevant keywords. Python, PyTorch, TensorFlow, NLP, LLM, specific models like GPT or Llama, transformer, fine-tuning, prompt engineering, RG, vector databases, MLOps, cloud platforms, responsible AI. Quantify your impact whenever possible. Improved accuracy by X%, reduce latency by YMs.
Showcase projects prominently. Tailor the resume.
Definitely. Detail the projects, the tech used, the outcomes, and absolutely tailor your resume to each specific job description, highlighting the most relevant skills and experiences. Make sure core software engineering skills are still visible too.
And interview prep. What should developers be ready for?
Be ready to discuss technical concepts in depth. LLM architectures, fine-tuning techniques like PEFT, RAG workflows, prompt engineering strategies like chain of thought, vector databases, evaluation metrics like BLEU or LLM, optimization methods.
Fundamentals too. Python, ML basics.
Yes, don't neglect the basics. Python coding, core MLDL concepts, NLP fundamentals like embeddings and attention, data structures, algorithms. System design questions are common too. How would you build a scalable LLM app?
And explaining their own projects.
Crucial. Be ready to deep dive into your portfolio projects, the problem, your approach, challenges, tech stack, results, and expect behavioral questions about collaboration, problem solving, how you learn.
So it's a comprehensive strategy in need of learning, building, connecting, marketing.
Exactly. It's a journey, but a very achievable one with the right approach.
Right. And to really bring all this together, the analysis you provided culminates in this ranked list, Table 5, the top 25 critical super areas for making this transition.
Yes, that table tries to synthesize everything we've covered. It ranks the 25 areas we think are most crucial, from foundational knowledge like Python and transformers, to advanced skills like fine-tuning and Org, through to operational aspects like LLMOps and cloud platforms, and finally the career strategies themselves. Each rank item has a rationale explaining why it's critical.
Well, this has been incredibly comprehensive, a real deep dive, as promised, into shifting into generative AI product development. The main takeaway for me seems to be, yes, the opportunities are huge, but it really demands a serious commitment to learning specialized skills way beyond traditional programming.
That's exactly right. Success here isn't just about knowing one thing, it's about a combination. Strong foundations, building those advanced skills through real projects, understanding the unique product lifecycle, navigating the fast-moving ecosystem, and positioning yourself strategically.
And certain areas really seem central model adaptation, like fine-tuning and RB, effective interaction through prompt engineering, understanding the core transformer architecture, definitely responsible development, and robust operations with LLMOps and optimization.
Couldn't agree more. Those are absolutely key pillars for anyone serious about building products in this space.
So for you, listening right now, as you think about this roadmap, maybe consider which of those 25 critical areas in Table 5 really resonates with your background. Where do your existing skills give you a head start? And maybe which area sparks the most excitement for you? Which part feels like the most compelling opportunity for your own growth and exploration in this, well, incredibly fast-moving world of generative AI?
Yeah, this deep dive, it's really just laying out the map, the actual journey. That's up to you, and it promises to be a fascinating one.